Okay, so hello everyone. I would like to thank the organizer, of course, for giving me the opportunity to present my work today. So I'm Mathilde Bouvier. I'm a postdoc at Leiden Observatory, and indeed I'm going to speak about sulphur-bearing species in NGC 253. But let me give you a bit of context first. So I will speak about the basic fact that in our universe, we can find the different shapes of galaxies and different types of galaxies, and this is due to the presence of the very various feedback mechanisms that are shaping them and that make them evolve differently. So one of these main feedback mechanisms, we can have the active galactic nucleus that you can see a schema of such an object here. It's usually accompanied by a powerful jets and outflow. There is also star formation feedback, where there are a lot of H2 regions, supernovae, clusters, supernovae remnants, and so on that will shape the galaxies. And also one of the other main feedback mechanism is the large-scale outflows and winds that we can find in the galaxies, and no matter if they are driven by AGN or starburst. So as you can see in the example of the starburst galaxy M92, it's the large-scale galactic wind that we can see. In particular, starburst galaxies are especially great laboratories where we can study feedback mechanism, and this is due to the fact that they present an exceptionally high star formation rates compared to other normal galaxies, such as our own galaxies. And the presence of such a high star formation rate is indicative of different physical conditions compared to the one that we can find in our galaxy. So if we want to understand how starburst galaxies are shaped and evolve, we need to be able to assess these physical conditions and how they are different from the one that we find in our own galaxy. So each of the feedback process I showed you before is usually associated to specific gas components, whether they are heated, dense, shock, turbulent, and so on. The thing is that in extragalactic environments, it's usually hard to disentangle this component. Because, for example, if we detect different species in the same spatially unresolved region, it does not always mean that they are tracing the same gas component. So what we need is, of course, powerful submillimeter interferometers such as ALMA, and there are recent efforts that succeeded to resolve the regions at the scale of giant molecular clouds, so a few tens of parsec in nearby galaxies, and even they succeed to resolve subregions, so less than 1 parsec scale. But still, with this high angular resolution, there are still multiple gas phase components of the ISM that are within one beam. So another powerful tool that we can use is actually astrochemistry, and in particular the multi-line multi-species analysis, because different species will be able to trace different regions, but one species can trace several different regions. So having a set of different species that are can help us to constrain the one specific gas component of the ISM. And we need the multi-line analysis because depending on the transition of the same species, it can trace different regions as well. So coming back to the feedback processes I was talking to you, each of them will trigger a unique chemistry and so a unique combination of molecular lines. So the idea is try to find what are the different states of what are the different combinations that we can use to determine a specific gas phase component. Today I'm going to focus on the sulphur-bearing species. So the main idea is that the main reservoir of sulphur-bearing species is on the surface of the Dug's grain. So if we want to have sulfur into the gas phase, there are mainly two main processes among various other, but the main ones are thermal evaporation and sputtering and shattering of dust grain in shocked region. And this is why sulphur-bearing species are usually ubiquitous in our galaxy and also in external galaxies. The advantage of these species is that also they are highly reactive into the gas phase, so their abundance will vary greatly on the thermal and kinetic properties of the gas. And lastly, they were proven to be very useful to reconstruct the chemical and dynamical history of the studied object. So for example, the abundance ratio of H2S, SO, and SO2 has been used as chemical clocks in shocks. So the main question we want to target are whether in starburst galaxies, which process dominates the release of the sulfur-bearing species into the gas phase, and hence to which physical condition it is associated. And also because of the specific tool that we can use with the sulfur-bearing species, we want to understand if they can tell us anything about the chemical and dynamical history of starburst galaxies. So for that, of course, we need to study starburst galaxies, and the perfect target is NGC 253. So it's the closest starburst galaxy. It has a large-scale outflow that is driven by the starburst activity and has no sign of AGN activity. Therefore, because of this high inclination, we can easily decompose the outflow component from the ISM component. So this galaxy is actually the best target to study the feedback mechanism of star formation alone. If we zoom in the 100 parsec near the central part of the galaxy, we have a schema here on the central molecular zone, in which there were 10 well-studied giant molecular clouds that were identified, which are the gray field shaped all over the CMZ. And you can see in the inner part it's even more busy with H2 regions, supernova remnants, and so on. And actually, there are recent studies that disentangled this inner part of the CMZ. So the 4 giant molecular clouds are actually decomposed into 14 superstellar clusters, which are all, associated with super hot cores. So thanks to the analysis of HC3N. And this galaxy is such a good target that it was the target of the alchemy survey. So Monica already introduced to you the survey this morning. So it's basically the first unbiased molecular survey towards the starburst environment. You can see the molecular richness of that has been detected towards the galaxy. The spatial resolution is the giant molecular cloud scale, so about a bit less than 30 parsec. There are several papers that were already published, so if you are interested in seeing what has been already detected and the studies that were already done, you can already find them in the archive. In this project, I'm focusing on sulfur-bearing species. These are the traditional targets among the sulfur-bearing species we chose. Of course, there are other more complex sulfur-bearing species that were detected, but I'm not going to focus on them now. So we first started to investigate the emission distribution of these sulfur-bearing species because maybe based on we wanted to see if there was difference in morphology. So here you have a moment zero maps for one transition for each of the sulfur-bearing species, H2S, CS, SO, and C2S. The upper energy level of the transition are more or less the same, so that we can see the distribution without any bias about the excitation conditions. In each of these moment maps, you have the position of the giant molecular cloud that I were presented to you before. The black hole is supposedly at the star position, and the triangle is where the kinematic center of the galaxy has been detected. So you can see that even though some species can be more or less extended than the other one, they all have the same behavior in the sense that they are going to pick more towards the inner part of the CMZ compared to the more external part. There are other species that are a bit different. So in the case of OCS and H2CS, we can see that it also pick well in the outer part of the galaxy, even though it is shifted from the giant molecular cloud. And we see that in the case of this species, we have a lack of emission that is relatively important in the central part of the molecular zone. SO2 is even different because it is detected only towards the inner part of the CMZ. So based on the first emission distribution investigation, we started to separate the species into 2 different groups based on their morphology. But as I told you, the same morphology does not mean that the species are coming from the same region. So the next step is, of course, radiative transfer analysis. Very quickly, we selected the 15 regions along the CMZ based on the previously defined giant molecular clouds if the species is peaking at the right position, so like the 10, 8, and 9. But we selected also new regions such as 2A, 1B, and 1A that are shifted from the previously defined giant molecular clouds to be able to take where the emission is peaking. And in the inner part, actually where there was the superstellar cluster I was telling you about, the emission is more consistent with superstellar cluster than with giant molecular clouds. So we extracted based on this superstellar cluster position. So we started by a basic LTE analysis with a rotational diagram. I'm going to show you the results for all of these species except for C2S and SO2. It's still under analysis. So what we see is that basically we see an increase of in the derivation of the rotational diagram towards the center, the inner part of the CMZ. So the inner part is within this orange rectangle. So we see that all of these species increase in the temperature, but as you can see, it's highly non-LTE or optically depth. There are optical depth effects. So the rotational temperature could be only upper limits. In the inner part, actually, there are two species for which we could derive two rotational temperature components, with the OCS one being particularly hot, more than 200 Kelvin. But we cannot really conclude anything about the temperature because the rotational temperature is not representative of the gas temperature. So we will have to do a step further into the analysis, going with the non-LTE analysis. We also tried to look at the line width to see if there are some correlation, because usually more species that are arising from the same gas tend to show the same line width. So in the outer CMZ, so here I show the line width of OCS as a function of H2CS and the one of CS as a function of H2S. So we see that the OCS is well correlated with H2CS and H2S is well correlated with CS. I do not show the other plots, but if we compare H2CS and CS, they are really not correlated. So it's a first hint that maybe OCS and H2CS could arise from the same gas component. If we look in the inner part of the CMZ, if we look in the inner part of the CMZ, the situation is a bit different because we have H2S that is well correlated with H2CS, SO, and OCS. And all of the species are not well correlated with CS. So the main result of this part of the analysis was that depending on whether we are in the outer part of the CMZ or in the inner part, we have different correlation between the species. In all the CMZ, CS has always the most broad line width. So it could be that CS is arising from a more turbulent regions than the other species. And if we look at the case of H2S, which is well correlated with CS in the outer part, but it's not the case in the inner part, it could be that depending on where we are looking in the CMZ, H2S could be put back into the gas phase via different mechanisms. So the situation is a bit more complex than it appears. So summarizing, in the outer CMZ, we found correlation between CS and H2S, which were actually based on the same group, based on the morphology, if you remember. And H2CS and OCS are also well correlated, and they were also looking in a similar way in terms of emission distribution. But in the inner CMZ, all of these species, no matter which group they are belonging to, they are all well correlated. So it really is a hint that maybe different processes are happening in the inner and the outer part of the CMZ. So to conclude, we detected several sulphur-bearing species. I'm still analyzing C2S and SO2. So stay tuned for that. And the main message here is that LTE analysis was not very conclusive. The temperature that we derived is not representative of the gas kinetic temperature. So the next step that I will perform is a non-LTE analysis, also to take into account the optical depth effect. And even further step would be to compare with chemical modeling to be able to fully comprehend the region of emission of the sulphur-bearing species. So it is still a work in progress, as you can see. So stay tuned for what comes after. Thank you.
Thank you very much, Mathilde. Speak on time. Let's see if there are questions or comments. Okay, we have one. Did you have a look at 34S isotopologues? Do you see same full width and maximum excitation or evidence for opacity effects?
So, so I have lines of S34O, yes. So I didn't look at the line width yet. I don't know if no. I think I put the LT analysis at some point. Sorry. Yeah, so this is the last two rotational diagram, and this is SO, and this is the isotopologue. So maybe the optical depth. So for sure, SO is optically thick. Because we have S34O, and also because we have other isotopologue of SO that are detected. Same for CS. So yes, but for the line width, I don't remember. I don't think I remember.
Okay. Other question? Okay. Okay, Quirino D'Amato, please.
Yes, thank you. So I'm not an expert of the local universe, but I don't know if this galaxy actually matches the definition of starburst galaxies. Starburst galaxy. I mean, I think it has like the star formation rate of a couple of solar masses per year. That is more or less the star formation rate of the Milky Way. Which is the advantage of I don't know if there are similar studies in our galaxy that should reach higher physical resolution, and which is the advantage of studying this kind of objects, another object with respect to the molecular clouds that you can find in our galaxy.
So so I guess there are multiple questions inside your question. So this NGC 253 is really considered as a starburst galaxy. So the rate of 2 solar mass per year is only in the central kiloparsec. It's not in the whole galaxy. So it's much higher. It's than our own galaxy. So that's why it's considered as a starburst galaxy. And the advantage of studying these galaxies is because so what we observe in our own galaxy, we observe them, and there are specific physical conditions, and it does not mean that we can project what we see in our galaxy towards the other galaxies. There will be different physical conditions by definition. It's not it's not always the same. So the advantage of studying starburst galaxies is to try to, in the end, get what are the differences with our own galaxies, how it changes, and how it affects the shape and the evolution of this particular type of galaxies. But you can do the study of also the AGN galaxy, and there are composites between AGN and starburst. So the idea is try to understand how the physical conditions change between the different types of galaxies. Did I answer you?
I'm biased towards probably like Euler galaxies in the. This
yes.
is just in my imagination, the starburst galaxy in the local universe. So it's just my bias probably.
Yeah, Euler got even more higher star formation rate. Yes.
Yes.
If quick, Stuart Villa.
Yes, thank you, Mathilde, for your talk. I was just wondering on the perspectives of your project, because you say that you're going to continue doing some stuff. So I'm just wondering if you are going to, for example, compare with PDR models or shock models to try to explain your observations.
Yes, so it will depend of what I find with the non-LT analysis. So what kind of density and temperature I found. The idea is also to compare with the shock tracers, HNCO and SIO that Monica presented this morning. So if sulphur-bearing species seems to be shock tracers, then I will compare with the shock model. We have an in-house model, UCL Chem here. Otherwise, I will use a PDR model if I see that it's more, the sulfur-bearing species are more consistent with PDR model.
Thank you.
So it will depend.
Okay, thank you very much, Mathilde.